Thank you. All right, we ready? Get a double dose of me today. Sure, that's exciting, right? We're going to do TCA cycle and electron transport chain today. So, I did notice I made a mistake here in the learning objectives. That should say alpha-ketoglutarate dehydrogenase complex. So that's the enzyme. But I think you guys would figure that out as you're reading through it, but a little mistake I made there. So yesterday we talked about glycolysis, right? And I think the way I'm going to approach TCA cycle and electron transport chain you're going to see are kind of similar. You may have seen these before if you've taken biochemistry, or sometimes they'll even talk about this stuff in like Bio 101 and things like that. But I'm probably going to approach it a little bit differently. So really I want you to know, just like when we did glycolysis, I want you to know what the purpose of the pathway is, what it's going to do. In this case, with TCA cycle, I mean, the general purpose is energy. It does provide some intermediates, some carbon skeletons that you can use for synthesis of other things. But its primary job, or the primary thing you think about with TCA cycle, is energy. So ultimately, we're going to use this to make energy. And we're going to talk about how we do that. Then how it's regulated. What are the things that are going to make it go slower or faster, or turn it on and off, if you want to look at it in a black and white way. Okay? And then how that might intersect with medicine. Okay? And that's what we're going to do. And just like with glycolysis, there's a few enzymes we're going to really focus in on, because those are the ones that control everything. And then the other ones we're not going to spend a lot of time talking about. We're going to go through them just so you can appreciate there's more than just the few steps we're going to look at. And some of those ancillary freely reversible reactions are absolutely critical for the TCA cycle, but because there's no control point there, it's not, and there's no diseases associated with it, we're not going to spend a lot of time on it. But it's where you're going to derive ultimately the energy in some cases. Okay, so an overview. TCA, I like saying TCA cycle. It flows off my tongue really fast. It's the easy way to say it. But you may see it called tricarboxylic acid cycle. That's what TCA stands for. Krebs cycle, citric acid cycle, they're all referring to the same thing. So if you learned it by a different name, that's fine. TCA is just much easier for me to say. So I'm calling it the TCA cycle. It's the final pathway where the oxidative metabolism of carbohydrates, which is what we already looked at. We looked at glycolysis, but also amino acids and fatty acids converge. So the way that the order I like to do is I like to do glycolysis, TCA, electron transport chain. You need to realize at the end, if you metabolize fatty acids, for instance, they're also going to go into TCA and electron transport chain. But once you're comfortable following a molecule of glucose, it's very, very, very simple to figure out how fatty acids or amino acids would actually fit into the pathway. So that's why I like to do it that way. The oxidation through the TCA cycle provides most of the energy that we're going to use to produce ATP. So we're actually going to produce ATP in the next lecture in the electron transport chain, but we're going to produce all the reduced intermediates that we're going to oxidize through the electron transport chain. We're going to produce those in the TCA cycle. Okay? There's other places where you produce them, but the TCA cycle produces the bulk of them. The cycle occurs in mitochondria, so the process we looked at earlier, glycolysis, that was actually happening in the cytoplasm. So what was our end product of glycolysis under aerobic conditions where we're going to do the TCA cycle? Pyruvate, right? So now I've got to get you guys that pyruvate is somehow going to get into the mitochondria in order to do the next steps. And so the TCA cycle occurs in close proximity and is linked to the electron transport chain, as you're going to see. And so ultimately, when we go through the TCA cycle, we produce these reduced intermediates. We're going to send them to the electron transport chain, and we're going to oxidize them through there. And I'll show you how that actually produces ATP. TCA cycle is an aerobic pathway, okay? At the end of the electron transport chain, you're going to have oxygen, okay? And we're going to make water out of it. If oxygen is not available, what's going to happen is all those things you're supposed to oxidize through the electron transport chain are going to build up, and they're going to stop the TCA cycle. Okay, so if you have a situation where you don't have enough oxygen, the TCA cycle is going to stop. Then what do you think is going to happen? If we go backwards and go to glycolysis, originally went to pyruvate, now pyruvate can't go into here, where's it going to go? Lactate, right? So when you have a lack of oxygen, one of the things you'll see is a lactic acidosis. Okay, and we'll talk a little bit more about that. So the TCA cycle does intersect with other areas of metabolism, and you can see, so here's the TCA cycle, and this is like one of those global pictures from your book, and it's highlighted right there, but you'll see there's things going in and out of the TCA cycle. It plays a big central role. So there's amino acids that will come in, provide carbon skeletons, or vice versa. If you need to make an amino acid, you can use a carbon skeleton from the TCA cycle, then you'll have to replenish it. But there's various areas. So some of the intermediates that we're going to see in the TCA cycle, you're going to see over and over again in other areas of biochemistry. So we have both catabolic pathways. We can break down amino acids, for instance, feed into the TCA cycle, or you can actually have anabolic pathways where you're actually going to synthesize amino acids. Heme is one we're going to see. Use succinyl-CoA to make heme, for instance. So the TCA cycle, as we're going to see, is going to start with oxaloacetate and acetyl-CoA. And then we're going to actually lose, and so here's just a general overview of what's going on. So we start with acetyl-CoA, oxaloacetate, we make citrate. Then as we go through, and actually at the very beginning of the TCA cycle, those are going to be critical steps. We're going to actually lose 2 carbons. So you actually lost, you have a net yield of 0 carbons there because you lost the carbons from the acetyl-CoA. And then you regenerate oxaloacetate. So the carbon skeleton, that oxaloacetate carbon skeleton, keeps getting used over and over and over again. And if you pull it out of there to make something, you just have to make more oxaloacetate to serve as a carbon skeleton. We talked about how you could do that yesterday. You can actually make it from pyruvate itself. So it is a cycle. Okay, and you're going to see this. You're going to see other cycles in biochemistry, and it's going to be the same thing. They're going to have a carbon skeleton. In this case, oxaloacetate is the carbon skeleton. You put the acetyl-CoA on there. You lose the carbons from the acetyl-CoA and eventually the CoA itself, and you regenerate oxaloacetate at the end. Okay, so in this case, we're actually, yesterday we talked about glycolysis first, and I'm actually going to talk about TCA cycle. There's something in between, which is the pyruvate dehydrogenase complex. Now, you don't have to go through this if you're breaking down fatty acids, for instance. You'll make acetyl-CoA from the breakdown of fatty acids directly, okay, or some amino acids as well. So this is unique to when you're starting with pyruvate. In this case, to keep the logical story, we were going through glycolysis, but other things, other amino acids can form pyruvate, for example. So strictly speaking, pyruvate dehydrogenase complex that we're going to talk about right now is actually not part of the TCA cycle. It's probably the only a pathway which is a single enzyme. So it's the link between glycolysis and the TCA cycle. Okay, or anything that can produce pyruvate in the TCA cycle. Could be some amino acids as well. What did I just tell you? The TCA cycle is actually going to happen in the mitochondria. Glycolysis happened in the cytoplasm. So one of the things we have to do is we're going to have to move that pyruvate at some point. So pyruvate dehydrogenase is actually in the mitochondria, so we actually have to move pyruvate in there, so you do have transporters. And we're actually going to convert that pyruvate into acetyl-CoA. Acetyl-CoA is the starting component for the TCA cycle. Acetyl-CoA and oxaloacetate. The oxaloacetate comes from the cycle. It's just there all the time, skeleton. So the acetyl-CoA is what's going to feed into it. So this is actually catalyzed. So the conversion of pyruvate to acetyl-CoA is catalyzed by pyruvate dehydrogenase. Now, it's also called pyruvate dehydrogenase complex. It's easier just to say pyruvate dehydrogenase. It's actually a complex of multiple enzymes. I think there's actually 5 of them in there. But there's multiple enzymes. Okay, it's a complex of enzymes. Just like a lot of things in biochemistry are a complex of multiple different proteins. It's a very complicated reaction, but we're not luckily going to get into the details of the reaction. So just recognize it is a somewhat complicated enzyme. Now, you do have to know some of these details I'm going to talk to you about with this enzyme. Now, you're going to see shortly there's another enzyme which almost does the exact same thing. So if you're comfortable with pyruvate dehydrogenase, the next enzyme we're going to see, you will already know everything about it because it's going to do the exact same thing, including having the same coenzyme. So once again, it's a complex. It's got multiple enzymes in there. It has 5 coenzymes, and you should know these 5. Okay, they're all critical components of the enzyme. 4 of the 5 are actually vitamins. So when you're trying to figure out what some of these vitamins do, this is a place where they come in. It uses thiamine. It's one of the 4 enzymes in the body that uses thiamine. One of the other ones we're going to see today as well. So you're going to see 2 of the 4 that actually use thiamine. Now, TPP, the thiamine pyrophosphate, is actually just the active form of thiamine. It uses lipoic acid. Now, lipoic acid isn't a vitamin because you can synthesize it. You can get it in your diet as well, but you can synthesize it, so it's not considered a vitamin, but it is going to act sort of like a vitamin in that it's going to be a coenzyme. Also uses coenzyme A. You remember that came from pantothenic acid. FAD and NAD+, so FAD from riboflavin, NADH from niacin. So you can start to think, well, what happens if I have a deficiency in any one of these vitamins? It's going to affect pyruvate dehydrogenase. And as you're going to see, it's going to affect one of the TCA cycle enzymes as well. Ultimately, what is that going to affect? The production of energy, right? So one of the consequences of having a low amount of one of those would be affecting energy production. And then from there, you have to say, okay, well, which tissues use the most energy? And we'll talk a little bit about that as well. So the actual reaction, we're actually undergoing an oxidative decarboxylation of pyruvate. So we're actually losing one of the carbons. So pyruvate has 3 carbons. We're going to lose 1 carbon right here as CO2, and then when we go through the TCA cycle, we're actually going to lose the other 2 carbons as CO2. So the CO2 you're breathing out comes from the TCA cycle and from this pyruvate dehydrogenase complex. You're also making NADH. We can use that NADH to actually make energy as well. So we can oxidize that NADH through the electron transport chain. So at the end, when we calculate the energy, we're going to actually use that NADH in our calculations when we're going from glucose completely oxidized through the TCA cycle. So how is this enzyme regulated? There's a couple ways it's going to be regulated. So I put this little chart together for you. Because in the green is supposed to be it's going to turn it on, and the red is supposed to be it turns it off. Now, I warn you that the figure in the text that I pulled out here, in my opinion, it made it much more complex. It's accurate. It's absolutely accurate. But it's getting a little more in-depth than you really need to know to understand it. So they're talking about a PDH kinase and a PDH phosphatase, and we're not going to talk about that. We're just going to talk about the enzyme and the things that turn it on and the things that turn it off. And for the most part, they're pretty logical. So The things that are going to activate it are going to be the substrates. So pyruvate is a substrate, NAD plus is a substrate, and CoA is a substrate. Those are all substrates for this enzyme. And then on the other end, what's going to be the product of this? Acetyl-CoA, right? So acetyl-CoA will deactivate it. So that's just substrate and product activation or deactivation. So they're going to play a role in controlling the enzyme. And then the other thing that's going to play a role is energy. Okay? So low energy would activate pyruvate dehydrogenase, and high energy would inhibit it. Remember, what we're doing here is we're sending pyruvate, we're converting it into acetyl-CoA, and we're going to use it for energy. You can also use the acetyl-CoA for other things, as we're going to see. You can make fatty acids, cholesterol, whatever. But right now, if we just think in terms of energy, that means if you have enough energy, you don't want to try to make more. And actually, you'll have multiple places where high energy is going to inhibit this whole process. So ADP would be low energy. I know in the other systems we looked at, like when we looked at PF, phosphofructokinase 1, okay, we had AMP. Here we actually have ADP, but they're both low energy forms of ultimately ATP. That's going to inhibit it. Or ATP is going to inhibit it. The low energy form is going to activate it. Sorry, I had that backwards. But you guys should have caught that anyway, right? You know that. Low energy is going to activate. And so you'll also see this other thing in here, calcium. So in muscle tissue specifically, you're going to see this with the TCA cycle and also what we're looking at right now, pyruvate dehydrogenase complex. Calcium is going to activate the pathway. Calcium indicates muscle contractions going on in muscle tissue. Okay, and it's going to turn on certain things. And one of them is the pyruvate dehydrogenase complex, try to start generating energy through this cycle. So ultimately, some of these things are going to be simple substrate, product inhibition or activation, and some of them are actually going to affect it allosterically. We're not going to look at the exact allosteric binding sites and what they activate and deactivate. There's a little more information there if you want to look. But what I've told you here in terms of pyruvate dehydrogenase activation and deactivation, if you can get that down, then you'll know all you ever need to know. And then you can also figure out if things go on in the body where certain of these things start accumulating on either side, what's going to happen. Okay, so that gets us to the point of having acetyl-CoA. And I already mentioned earlier, that's what you need to start the TCA cycle. So acetyl-CoA can come from other things, which you'll see later on, oxidation of fatty acids, for example. But the first true step in the actual TCA cycle itself is the formation of citrate from acetyl-CoA and oxaloacetate. Oxaloacetate is just that carbon skeleton. It's going to be used over and over in the TCA cycle. So the acetyl-CoA is the new thing coming into the TCA cycle. So as we go through this cycle, you're going to see 3 irreversible steps. Sounds very similar to what we did with glycolysis. Those are going to be the 3 key steps. So this is one of the key steps in the whole process. This is one of the regulated steps. This is also an irreversible step. You'll notice the arrow only goes in one direction. Okay, so the 3 steps we're going to spend a lot of time talking about are irreversible. It's regulated simply by substrate activation or product inhibition. If acetyl-CoA starts building up, and assuming you have oxaloacetate available, which you should because you keep using it over and over, if acetyl-CoA starts building up, you're going to activate the TCA cycle. If citrate starts building up, you're actually going to inhibit the process. We also saw citrate inhibiting something else, right? If you've already looked at your stuff from yesterday. What did it inhibit? Yeah, PFK1. So this is where citrate is. So if citrate starts accumulating, what does that tell us? It tells us the TCA cycle is not going. What does that mean? Well, we're building up all these high energy intermediates, we better shut down glycolysis. We don't need to keep lysing glucose. We can do something else with it. Okay, so you'll also see that citrate, when you go to make fatty acids, you'll actually use citrate to make fatty acids. That's where you can use acetyl-CoA to make fatty acids, but where it comes from is the citrate. Okay, so that's the first step. It is one of the three key enzymes in the actual TCA cycle that I do want you to know. It's not real complicated how it's actually regulated, though. And you'll notice, just like when we did glycolysis yesterday, there's some steps I'm not going to spend a lot of time. I want you to realize there's multiple steps in there, but you don't have to try to memorize the enzymes, nor do you have to memorize what the substrate and product is. Okay, so just to be complete, I'm including those in there. In this case, it's just an isomerization reaction. So as a biochemist, that's actually kind of boring. But the next step's super exciting. Okay, so in the next step, we're actually going to oxidize and decarboxylate the isocitrate. Okay, so this enzyme is one of the key enzymes. You'll also notice the arrow goes only in one direction. It's isocitrate dehydrogenase. Considered the rate-limiting enzyme in the TCA cycle. Depending on which resource you look at, they may consider the three key steps we're going to talk about today. All could be considered rate-limiting to a certain extent. Your textbook considers this to be the rate-limiting step. Any one of them, if you inhibit, it's going to inhibit the pathway. So it's not the same as some of the other pathways. But if we inhibit right here, what's going to accumulate? Well, we can accumulate citrate, so we can actually make fatty acids, right? And we can, all that energy that's built up because this pathway is inhibited, we can use to also make fatty acids. So it's a good spot to actually have a control step. So rate-limiting enzyme, or rate-limiting step of the TCA cycle, we're going to take isocitrate and make alpha-ketoglutarate. Now, in that process, you're actually also making NADH. This is one of our steps where we're making NADH. NADH is a high-energy compound. We're reducing NAD+ and making NADH. That NADH is going to feed into the electron transport chain, as we're going to see. We're going to derive energy from it. You also, this is one of the steps where you're actually going to lose carbon dioxide again. The carbon from acetyl-CoA coming in there is going to be lost. So you end up with a net carbon gain or loss through the TCA cycle of 0. Okay. So the carbon coming in from acetyl-CoA gets lost. There's going to be 2 of them. Here is one of the steps. Okay, since this is our rate-limiting step, it only goes in one direction. It's going to be a control point. What are the things that are actually going to control this step? Once again, I think you could use logic to a certain extent. There is a certain amount of memorization in some of the cases where you have to remember the specifics, but one thing with all these pathways to keep in mind is, and a lot of times with a multiple choice question, this can help you at least narrow down, if not answer the question, is just think about, when would TCA cycle be active? When you need energy, right? So high energy things are going to inactivate it, low energy things are going to activate it, just like with glycolysis, okay? So low energy, ADP is going to activate it. High energy, ATP is going to inactivate it. Now, NADH is the reduced intermediate. That's actually the high energy form. That actually inhibits it. It's also a product of this. So this is an example also of product inhibition. So if NADH starts accumulating, TCA cycle is going to stop. Okay, that's an important point. TCA cycle is going to stop if NADH starts accumulating. So anything that accumulates NADH, for example, if something's blocking the electron transport chain, which is normally where you'd oxidize that. So what do you think is going to happen if that happens? Things are going to back up to glycolysis. Then what's going to happen? How can you regenerate NAD plus in glycolysis? Go from pyruvate to lactate, right? So once again, you'll get a lactic acidosis. Calcium from in muscle tissue specifically, calcium is going to activate the TCA cycle. Once again, calcium indicates muscle contractions going on. We need energy. Okay. Okay, so the next step, also arrow going in one direction. So this is going to be our third step. Okay, so there's only really 3 major enzymes that we need to know in the TCA cycle, and this is the third one. So they all occur right at the very beginning. So you had your citrate synthase, isocitrate dehydrogenase, and alpha-ketoglutarate dehydrogenase. It's also called alpha-ketoglutarate dehydrogenase complex, similar to pyruvate dehydrogenase complex. If you look at the reaction, if you get excited about that kind of thing, if you look at the details of the reaction, you'll see they're catalyzing almost the same reaction. They're just starting with a slightly different substrate. So these are actually very, very, very similar enzymes. So if you're comfortable with pyruvate dehydrogenase complex and the cofactors, we're going to use the exact same cofactors here. So those 4 vitamins, you had thiamine, NAD+, FAD, and pantothenic acid or coenzyme A. Those are all cofactors for this, as well as lipoic acid, which is not a vitamin because you can make it, but so it requires all the exact same cofactors as pyruvate dehydrogenase complex. Once again, if you get a deficiency in any one of those, you're going to inhibit pyruvate dehydrogenase and the TCA cycle itself. So you're going to inhibit the ability to make energy. So this is also a key step. It's irreversible, and it is regulated as well. In muscle tissue, it can be activated by calcium, just like isocitrate dehydrogenase can be activated by calcium. Okay, and that's because it's indicating muscle contractions going on. We need energy. It will be deactivated. In this case, if you look, both of those are products of the enzyme. Succinyl-CoA is a product of the enzyme, and NADH is a product of the enzyme. NADH is also a high energy compound. So if NADH builds up, it'll also inhibit, pyruvate dehydrogenase complex. It'll inhibit isocitrate dehydrogenase and the alpha-ketoglutarate dehydrogenase complex. All of them will be inhibited by the buildup of NADH. Okay, so that seemed like a lot, and we're just a little bit halfway through the lecture. That's because all the complicated steps were all piled right at the very beginning. So the rest of the steps are going to be important for some reasons I'm going to talk about, but we don't have to memorize the enzymes. Okay, we don't. Now the substrates, it's up to you if you want to memorize them or not. If you feel like this is biochemistry, I got to memorize something in bio. I got to memorize some cycle to feel comfortable. I would say out of anything in biochemistry, the TCA cycle would be the one you want to memorize because many of the intermediates you're going to see in other pathways. You're going to see malate, you're going to see fumarate, okay? You're going to see succinyl-CoA. You're going to see these things used in other pathways again. And when we talk about those pathways, I'm going to ask you, where did we see that before? And immediately you'll be like, oh yeah, TCA cycle. Ask me a hard question, come on. But anyway, so we're going to fly through some of these steps. And just make note of the things that I want you to notice, okay? So cleavage of succinyl-CoA. So here's an enzyme, succinate thiokinase, also called succinyl-CoA synthetase. What I want you to get out of this is we're actually making GTP here, okay? So there is a substrate level phosphorylation going on, just like what you saw in glycolysis. So we do make a GTP directly. And GTP can be converted to ATP and vice versa. So it's an ATP equivalent. So there is one ATP equivalent made directly in the TCA cycle. All the rest of the energy is going to come from the reduced compounds that we're going to make that we're going to oxidize through the TCA cycle. So we've already made some NADH, right? We're also going to make some FADH too, as you're going to see in the next step. So we're getting a GTP there. We're going to oxidize succinate to fumarate. Once again, you're going to see these compounds over and over again. Succinate dehydrogenase is the enzyme. This is a weird enzyme because this is also complex 2 of the electron transport chain, as we're going to see. So it's actually part of the electron transport chain and part of the TCA cycle. So this, the important thing here, though, is that we're actually making FADH2. So we've already made some NADH. Now we're making some FADH2. This will also go, is a high energy compound, will go into the electron transport chain. Okay? Once again, hydration of fumarate, not too interesting, can go in both. You see all these reactions I'm talking about, they can go in both directions. The only thing I'll tell you is you will see fumarate, you will see malate in other pathways. You will see those substrates over and over again, but we don't have to try to memorize this reaction. And you'll also see, okay, in this last step, we're actually converting malate to oxaloacetate. You'll see oxaloacetate and you'll see malate over and over and over again in other places, going in both directions. Sometimes we're going from malate to oxaloacetate, sometimes we're going OAA to malate. So we're generating NADH again, so we're generating ultimately something that's going to be used for energy. So we keep, as we're going through, we're performing all these oxidations and we're coupling them to reducing things, and these reduced compounds are the high energy things that we can actually oxidize through the electron transport chain. And we've actually now completed the cycle. So now we're back to oxaloacetate. So now we can actually bring in another acetyl-CoA with that citrate synthase and begin the cycle all over again. Okay? So I went through those steps fast because we don't have to memorize the enzymes. I just want you to realize, you know, we're going through there, we're making NADH, we're making FADH2, we're making a GTP in there, okay? And that's about the extent. And I wanted you to appreciate that there is other steps in there. Okay, so the energy produced by the TCA cycle. Okay, so in order to ultimately what we want to use for energy is ATP. Some reactions you can use FADH2 or NADH for energy to drive a reaction, but most of the time we want ATP to use for an energy source. And I told you ultimately we're going to send things through the electron transport chain to derive that ATP. When you do that, when you send things through the electron transport chain, for every NADH you send through the electron transport chain, if things are working perfectly, which they don't always, but if things are working perfectly, we're going to get 3 ATP. So if we start with 3 NADH, we're going to get 9 ATP. So if you remember, as we went through that TCA cycle, 2 of the big regulatory steps, isocitrate dehydrogenase and the alpha-ketoglutarate dehydrogenase, you had NADH produced there, and then there was another step later on. We didn't spend a lot of time also producing NADH. So we get 3 from there. Ultimately, if things are working perfectly, you can get 9 ATP from there. We also produced FADH2. It can also enter the electron transport chain. Each FADH2 produces 2 ATP. Now I'm going to show you in the next lecture when we go through the electron transport chain why you can get 3 from NADH and why you only get 2 from FADH2. At least I'm going to attempt to do that. If I forget to tell you when we get there, I usually don't forget. If I forget to tell you, remind me and say, hey, you forgot to tell us. It'll probably become clear to you anyway. We also produce a GTP. We have a substrate level phosphorylation during the TCA cycle, so that is an ATP equivalent. You can convert GTP to ATP. So for each acetyl-CoA that enters the TCA cycle, you're actually going to ultimately produce 12 ATP if things are working perfectly. Now we can actually use that same math and calculate the energy produced by completely oxidizing 1 molecule of glucose. So that means we're starting with glucose, we're making pyruvate, we're sending it to pyruvate dehydrogenase complex, making acetyl-CoA, sending that acetyl-CoA through the TCA cycle. So at that point, every carbon that started in that glucose molecule is lost as CO2. So you've oxidized it completely. So how much energy do we get there? So from glycolysis, if you remember glycolysis, we got 2 ATP, right? You got a net 2 ATP. You had to start with 2, but you got 4, so you netted 2. You also remember, if we're under aerobic conditions, you have that NADH that's generated during glycolysis. We can actually oxidize that also through the electron transport chain. Okay, and I told you a second ago you can get 3 ATP per NADH. So glycolysis itself will provide 2 ATP directly and 6 ATP indirectly from the oxidation of NADH. So we can actually get 8 ATP there. When we send pyruvate into the pyruvate dehydrogenase complex, we convert it into acetyl-CoA, we also generate NADH. And we'll generate 2 NADH because you'll make 2 pyruvate molecules for every glucose, right? Because we split it in 2 and each 3 carbon went through. So we produce 2 molecules of pyruvate for every molecule of glucose. So we get 2 NADH from every molecule of glucose. So So we send 2 pyruvates through this pyruvate dehydrogenase complex, we get 2 NADH. Once again, those can go in the electron transport chain and generate 3 ATPs themselves. So there's another 6 ATP. Okay? So from a molecule of glucose, so we're going to lose one of the carbon skeletons right there in that pyruvate dehydrogenase complex. Now we have a 2-carbon skeleton, acetyl-CoA. So from each molecule of glucose, you end up with 2 acetyl-CoA. So each acetyl-CoA makes 12, right, as it goes through the TCA cycle, assuming everything's working perfectly, so you get 24 there. So if you add everything up at the very end, you get a total of 38 ATP per molecule of glucose. Now, some of you who've taken biochemistry before may have heard a different number. Who's heard a different number? Heard a different number, right? Okay. So I don't want to confuse you. This is under ideal circumstances. Okay? This means, first of all, the electron transport chain is working perfectly, which it doesn't always do. But the other thing where I kind of fudged the numbers a little bit is in this glycolysis, this 2 NADH. You remember glycolysis actually happens in the cytoplasm. We actually have to move that NADH into the mitochondria before we can oxidize it. So you actually lose a little bit of energy there. So you may have seen the number 36. Some people will do the calculation and come up with the number 34. It depends on how many ATP you're... So the whole reason for the difference there is how many ATP you're getting from the NADH produced during glycolysis. So I'm using 3 as a number. Sometimes they'll use 2.5, or sometimes they'll use 2, and they'll come up with 36 or 34. Okay, so if you've seen a different number before, that's why. Okay, and technically the 34 or the 36 would be much closer to reality. You're never really going to get 38 because you're not going to get the full 3 ATP from NADH. Hopefully when we get to the electron transport chain and you kind of see how it works, you can see how the stoichiometry is never going to be exact. So these are all estimates. Sometimes the electrons don't go perfectly and they go off and kilter and they actually cause issues, but it also ends up reducing the amount. So we're assuming under ideal situation. So the nice thing about this figure is it kind of summarized everything that we talked about. It took out all the unimportant enzymes, I call them, but at least the enzymes we don't have to learn. The enzymes, so all 3, the 3 irreversible, and you'll notice right in there, you can see there's 3 irreversible steps. Those are the 3 key enzymes. Citrate synthase, regulated by the accumulation of citrate. Isocitrate dehydrogenase, we've got the things that activate or deactivate it. Low energy is going to activate it. High energy is going to inactivate it, right? And then calcium is going to activate it in muscle. Same thing with alpha-ketoglutarate dehydrogenase complex. So this is a useful figure to study from if you like to have a picture. not useful to teach the whole cycle from, but at the very end, it kind of summarizes things nicely. The only other thing I'd like to see in that picture is I wish they could really make it show you everything you needed to know. If it would show you the NADH, the FADH2, and the GTP that are actually being made there. That's really the only extra information you would need to add to that, and then you have all you need to know about the TCA cycle. Okay, so we're going to talk a little bit about the TCA cycle and how it intersects with human health. First thing we're going to talk about is arsenic poisoning. If you remember, we actually mentioned arsenic poisoning yesterday when we talked about glycolysis. So there was that step in glycolysis where that inorganic phosphate came in and was attached to that carbon skeleton, and ultimately you use that to make an ATP. And arsenic could substitute there, okay, and then therefore you didn't get that phosphorylation event, and the arsenic spontaneously fell off, so that didn't really cause an issue other than you got one less ATP, but if you get one less ATP, you end up with a net yield of 0 from glycolysis. But in most tissues, that's not too big a deal. As long as everything's flowing through, we can still go into the TCA cycle and make energy, right? But, and this is where the true arsenic poisoning comes in. This is where arsenic is actually going to kill you, okay? So arsenic actually reacts also with lipoic acid. And when it reacts with it, it renders it, basically it destroys it. As far as the body is concerned and the enzymes that use it, it's been destroyed. So it's no longer there and it no longer can be used, therefore you don't have the coenzyme. So what were the two enzymes that needed lipoic acid? Pyruvate dehydrogenase complex and alpha-ketoglutarate dehydrogenase complex. Therefore, it's going to inhibit both of those enzymes. So what's going to happen? Well, you can't make energy, okay? You can't make energy from glycolysis. Well, you can make energy from glycolysis. You can't make energy, you can't feed that pyruvate into the TCA cycle, but also other things you're going to oxidize, like fatty acids that are going to feed into the TCA cycle. They can't go either. You inhibit the TCA cycle directly and also the pyruvate dehydrogenase complex. So, therefore, you can't make energy, you're going to die. Okay, so it affects the tissues that require energy the most more directly or more quickly. So that includes things like your brain and muscle. Anything that's going to use a lot of energy is going to be inhibited very quickly. So that's what happens in arsenic poisoning. The TCA cycle, in order for the TCA cycle to keep going, to keep working, all those reduced intermediates, the NADH and the FADH2 that we built up, they have to be oxidized. If they're not oxidized and they accumulate, the TCA cycle shuts down, right? And you had those key regulatory steps that you saw, the isocitrate dehydrogenase and alpha-ketoglutarate dehydrogenase. You saw those enzymes are inhibited if NADH builds up. Anything that inhibits the electron transport chain, which can include, for example, a lack of oxygen, will ultimately inhibit the TCA cycle. So if you stop breathing, that TCA cycle is going to stop. Okay? What happens when the TCA cycle stops? I've said this multiple times now. The TCA cycle stops, got these reduced intermediates building up. It actually ends up feeding back. Right? If NADH builds up, you're not going to go to pyruvate dehydrogenase complex. You're not going to go from pyruvate to acetyl-CoA. So where's that pyruvate going to go? Lactate, right? Goes to lactate. So you'll see a lactic acidosis as well. Okay? Multiple vitamin deficiencies. Pyruvate dehydrogenase and alpha-ketoglutarate dehydrogenase required 4 vitamins, right? They had 5 coenzymes. Lipoic acid was the other one, which is not a vitamin, but you had thiamine, NAD+, FAD, and coenzyme A, right? And they're all ultimately derived from vitamins. So a deficiency in any one of those is going to affect the production of energy. It's going to affect pyruvate dehydrogenase complex and alpha-ketoglutarate dehydrogenase complex. Okay? So ultimately, you can also figure out, well, if you have a deficiency in one of those, lactic acidosis would probably be a symptom, right? Because you're going to inhibit those pathways. Also, you can figure out that, well, it's probably going to affect, when we're talking about vitamin deficiencies here, usually they're a little more subtle than something like a lack of oxygen. So you're usually not have 100% vitamin deficiency, so it's a little more subtle here. But you're going to start inhibiting your ability to produce energy, and that's going to affect the tissues that use a lot of energy. For example, nervous tissue. So you see neuropathies, myopathies, muscle tissue, including cardio tissue. Now, some vitamin deficiencies are more common than others. Out of those deficiencies, or out of those enzymes, the most common one that you'll actually see would be a thiamine deficiency. And we actually already talked a little bit about a thiamine deficiency because we already, in this lecture series, you already saw the vitamins. So what is a thiamine deficiency? There's actually a couple things it can cause. There's one version from alcoholics, which was what? Wernicke-Korsakoff syndrome, right? Which is what I've got there. You also had beriberi, which is primarily a dietary deficiency. But Wernicke-Korsakoff, just to remind you, encephalomyopathy or encephalopathy, psychosis syndrome, starts with Wernicke's encephalopathy and then progresses to Korsakoff syndrome where you see the psychosis. And it's a deficiency in thiamine. Okay, so it starts affecting your brain. And you also see some of the symptoms are actually effects on muscle as well. That the stigmas, that's an effect on muscle. Okay? So tissues that use a lot of energy. You can also have a genetic deficiency in the pyruvate dehydrogenase complex. And a genetic deficiency in pyruvate dehydrogenase complex is one of several possible causes of Lee syndrome. Okay, this has also got it's also sometimes called subacute necrotizing encephalomyelopathy. It's much easier to say Lee syndrome. But you can see from the name, it's necrotizing encephalo-brain myelopathy, spinal, so it's affecting the brain and the other nervous tissue. Okay, once again, they rely heavily on the brain and nervous tissue relies heavily on energy produced from glycolysis into the conversion of pyruvate to acetyl-CoA and the TCA cycle. So your brain, you can't cross the blood-brain barrier with fatty acids. So your brain is relying on glucose and/or ketone bodies if they're available. It's usually just glucose. So that's why it's going to affect that tissue more than others. Lee syndrome, there's actually multiple different things that could cause Lee syndrome, and I'm going to mention Lee syndrome again in the next lecture. It's a very severe condition. Once again, if you think of what's going to happen if you can't convert pyruvate to acetyl-CoA, where's pyruvate going to go? Lactate, right? I've said this over and over. So you do get a chronic lactic acidosis. You get that neurodegeneration, so you get that necrotizing encephalomyelopathy. Muscle spasticity, once again, you can affect muscle's ability to generate energy. And most forms actually, I said some forms, most of the forms actually result in an early death within our first couple years of life. There are adult onset versions of Lee syndrome. And once again, because of the brain relying on the TCA cycle, in this case, relying on the complete oxidation of glucose through the TCA cycle, it's going to be affected the most severely. Okay, so see you guys in about 10 minutes for the next in this super awesome series, right?